So welcome to day 2. Kenneth, the floor is yours.
Okay. So hello, everyone, and welcome to the second day of the QBronze Entangling Workshop. So yesterday, we looked at the basics of classical systems, and today we're going to be going over quantum systems. So before I jump into the content for today, I'll just do a brief recap on things we covered yesterday. Okay. So yesterday we started by seeing what a bit was, and we said a bit is the smallest unit of useful information that can be stored in a classical computer. And from there, we started looking at operations we could apply to change the value of our bit. So we looked at 4 operators: identity, negation, 0, and 1. And this is how they work. Identity doesn't really do anything. The input and output values are the same. Negation, or the not operator, flips the value that we provide as the input to the other one. So if we are to provide 0 as our input, we'll flip it to the value of 1. And if we are to provide 1 as our input, we'll flip it to the value of 0. Then for the 0 operator, regardless of the input you provide it, it's always going to have 0 as its output. And similarly for the 1 operator, regardless of the input you provide it, it's always going to have 1 as its output. So from there, we moved on to take a look at the transition tables. And these transition tables help us understand how these operators work. So in a transition table, up here, or in transition table, up here, we have the initial states. So our initial states are the input values. So we can have either a 0 as the input or 1 as the input. And finally, we have the final states. So these are the output values. So we can either have 0 as our output or 1 as our output. And from there, we make use of the entries within the table. So the entries within the table are probability values. And we have a 1 written here. We have a 1 written here to indicate that if 0 is our input, then 1 is going to be our output. So the 1 we have written here is the probability that if we start off with 0, we're going to get 0 at the end. So this is definitely what is going to happen. And here, we also have a value of 1, which is trying to say if 1 is our input, we're definitely going to have 1 as our output. So we looked at the transition tables for all the operators. And we said from these 4 operators, identity and not are the only reversible operators. From there, we moved on. Okay, so the 4 operators we just looked at are deterministic operators. So given a specific input and the operator, we know the output. But now we're looking at probabilistic operators, whereby given the inputs and the operator, the output is not certain. Okay, so here we have an operator, which is the operator of a fair coin toss. So we have the initial states, or our input values here, and the final states. So 0 here, so because we're referring to a fair coin toss, 0 here denotes head, and 1 here denotes tail. Similarly here, 0 here is for head, and 1 is for tail. And these are the probability values. So if we have our coin facing head and we are to toss it, half of the time we'd expect it to land on head, and half of the time we'd expect it to land on tail. So the thing is that sorry. Okay, so the thing is that it's possible that we're given an operator, but we don't know the actual entries in our operator, and we might want to figure this out. So one way we can go about doing this is to apply our operator several times and see the results we get. So in this case, we could take the operator seen here. So that is the fair coin toss operator, and apply it to our coin facing head a couple of times. So we could try this, let's say 100 times, 1,000 times, 10,000, as many times as we want. And the thing is that the higher the number of times we apply our operator, the closer we get to understanding what the actual probability distribution is going to be. Yeah, so the higher number of times we apply our operator and retrieve the results, the closer we're going to get to understanding what the entries in our operator consist of. Okay, then we moved on to looking at the coin flipping game, where we have 2 biased coins. And we have a game here such that for our first biased coin, which is a euro coin, we start off by tossing it. And if it's to land on head, we're going to flip the euro once more. But if it's to land on tail, then we're going to flip the cent coin. So the entries here can be used to create an operator. So the operator we have here is the operator for tossing our game coins. And unlike the case where we were looking at for the fair coin toss, for this operator, we have some form of dependence. So the outputs of our current source, or the probabilities assigned to the outcomes for our current toss depend on what we got from the previous toss. Then we moved on to look at probabilistic states. And as we've been talking of tossing coins thus far, we can have a probabilistic state here to represent the information regarding a fair coin toss. So here, we've tossed our coin, and the entries in the vector you see here are for the different outcomes we could get. So the first entry is the probability that our coin will land on head. And the second entry we have here is the probability that it lands on tail. So we can also have a biased coin where you see we have a higher probability that it lands on head, as you can see here. So we're not just restricted to 2-dimensional vectors. We can have vectors with several entries. and each entry can be assigned to some event or to the outcome of some event. Okay, then we went on to look at probabilistic operators. So because we have probabilistic states as vectors, we now have probabilistic operators in the form of matrices. And by performing matrix vector multiplication, we can change the values in our probabilistic states. So we could have a probabilistic state that represents a bias coin. And when we apply some probabilistic operator, we get a new probabilistic state with new entries for a different bias coin. Okay, then we went on to look at two probabilistic bits, whereby instead of dealing with separate coins or separate probabilistic bits, we can combine them. So we do that by taking a tensor product. So initially, we have two-dimensional vectors here. But if we are to combine our system, or if we are to create a composite system, we're going to get a four-dimensional vector where the entries will be such that what's on top here will be the probability that both land on head. The next entry would be head, tail, then tail, head, and finally tail, tail. And we also looked at combining probabilistic operators. So the operator we have here is a 2x2 matrix, and we can apply this to a single probabilistic bit. And the operator we have here is also a 2x2 matrix, which you can apply to another probabilistic bit. So if we are to combine our probabilistic bits, such that we have the composite system you see here. So we have four entries here. So if that is the case, we can also combine our operators. So now we have a 4x4 matrix and a four-dimensional vector, and we can now perform the matrix vector multiplication to alter the entries in our probabilistic state. Okay, so that's a brief summary of everything that we covered yesterday. So now we can move on to quantum systems. So we're going to start off by looking at flipping a quantum coin. Okay. So before I start off, for those, okay, so we might have people that aren't too conversant with quantum mechanics or the term quantum or quantum theory. So the most basic way to describe this is to say for our classical systems, we're dealing with macroscopic objects, but now that we're talking of a quantum system, we're dealing with particles at the atomic or subatomic scale. So we have an experiment here. That sets up our version of a quantum coin. That sets up our version of a quantum coin and tossing it. So this is how it's going to work. we have photons. We have a photon source providing us with photons. We have a beam splitter, and we have detectors. So we can think of our photons as coins, and then the beam splitter will be the act of tossing our coin. And then finally, the photon detectors can be thought of as our coin landing, and we can actually check to see if it landed on head or tail. So this is the experiment here. So we have a photon source, and the photons coming from this source can be thought of as coins, and they hit the beam splitter. So the beam splitter is the act of tossing our coin. And there are two possible things that can happen when the photon hits the beam splitter. It can either be reflected or transmitted. So if it's reflected, we can think of this. So if it's reflected and it hits the detector, we can think of this as our coin landing on tail. And if it's transmitted and it hits the detector, we can think of this as our coin landing on head. Okay, so our beam splitter behaves similar to a fair coin toss. So there's an equal probability that it's transmitted and reflected. So as you can see, if it's transmitted, we can think of it as our coin landing on head. And if it's if it's transmitted, we can think of it as our coin landing on head. And if it's reflected, we can think of it as our coin landing on tail. Okay, so we've introduced our numbers here, so the states. So we have the state 0 here for head, and then state 1 for tail. And we've even replaced the beam splitter with coin flipping. Okay, so we have an experiment here, and so we are to toss our coin. So we have our coin facing head, and we're going to toss it. So there is some probability it could land on head and some probability it could land on tail. And then if it's to land on tail, we're going to do nothing. But if it's to land on head, we're going to toss it once more. And there is some probability it could land on head and some probability it could land on tail. So you can think of the mirrors here as the identity operator. So the R is going to change. The R is going to change the states. So what is the probability that the final state is state 1? Or what's the probability that at the end of the experiment you see here, our coin is tail? So you can type in the chat. We have an experiment here where we're going to toss our coin. So state 1 here represents head, and this is the first coin toss. So there's some probability it could land on head and some probability it could land on tail. So if it's to land on tail, after the first toss, we're going to do nothing. But if it's to land on head, we're going to toss it once more, and it can land on head or tail. So what's the probability that it lands on tail after the experiment you see here? Okay, so I'm seeing 75%, 25%. Okay, so 75 and 25, they weren't assigned to any specific outcome. So any other takers, any suggestions on what the probability that we end with tail at the end is going to be. Okay, so I'm seeing head 75% and tail 25%. Okay, I'm also seeing 50-50. Okay. Any other suggestions? So the coin flipping operators you see here, it's for a fair coin toss. So the coin flipping operators you see here, they represent a fair coin toss. They are for tossing a fair coin. Okay, so I'm also seeing 50-50 and 60-20. Okay, so let's see what the solution might be. Okay, so here, so let me scroll down a bit. Okay, so from the first toss, so we said this is tail. So from the first toss, because this is fair, okay, this is a fair coin toss, and this is a fair coin toss, and we have only two possible things that can happen. Either our coin will land on head, or our coin will land on tail. And we said the probability that lands on tail is 50% here. So if it's to land on head, we're going to toss it once more. And there is some probability it could land on head and some probability it could land on tail. So from the first toss, there is a 50% chance it lands on tail. And if it is to do that, we're going to stop there. If it lands on tail, we'll stop there. But if it's to land on head, we're going to toss it once more. And there is a 25% chance at this point that we get head at the end. So there is a 25% chance we get head at the end, and also a 25% chance we get tail at the end. So we can just sum these. So we have 50% here and 25% here. So our final values are 75% and 25%. So the probability that lands on tail is 75%, and the probability that lands on head is 25%. Okay, so we're going to try a new experiment here. And in our new experiment, we're going to perform two coin tosses. But in this case, we perform the first toss. So we perform the first coin toss here. We're starting off with head. And we're going to perform the first coin toss, where the probability it lands on head is 0.5 and the probability it lands on tail is 0.5. And then we're going to perform a second toss. So at this point, what's the probability that we end up with head? So what's the probability that after the two coin tosses you see here, what's the probability that we end up with head? Okay, so I'm seeing we have a question from Manuel. Let me see. So I don't know if someone could read it out for me. I don't think I can access the question. I can't see it anywhere.
Can you read it from Discord, Tricia?
Yes, it's not from Discord. It just raised his hand here in the webinar, so but I allowed him to talk. Do you prefer, Manuel, posting your question on Discord? Or you allowed to talk if you like?
Yeah, you go ahead and ask your question, Manuel. You need do we have to
Yeah,
unmute?
Manuel, you are allowed to mute yourself.
Okay, sorry, I didn't get that. But okay, first of all, before we even get to the question from Manuel, I'm seeing another question in the chat concerning the time it takes for the signal to travel. Okay, so forget about the actual experiment. What we're discussing here is just tossing coins. So we set up the analogy here where we're tossing coins. So yeah, don't bother about the time it takes anything to be done or the distance or anything like that. We're just talking of tossing coins. Okay, so sorry, like back to the question from Manuel. So if you can be granted access to, okay, I think it was an accident.
Yeah,
So
to go on.
Okay, great. I'll just continue. So from my earlier question, so what's the probability that we end up with head after 2 coin tosses? Okay, so I'm seeing 50%, 50, 50%. Okay, 75%, 50%. Okay, so let's scroll down and see what you actually get. So yes, this is actually what most people predicted, that we're going to have a 50% chance it lands on head and a 50% chance it lands on tail. But this is what we actually get from the results of our experiment. So we tossed our coin twice, and every single time it landed on head. Okay, so I'll just give you a second to think about this. So imagine picking up a coin and you are to toss it twice, and every single time you do this, it's always going to land on head. So that's like some really weird behavior. And we're now going to start looking at quantum systems to explore or to understand why we're getting the results we see here. Okay, so okay, so let's look at the Hadamard operator. So in the experiment we just saw, where we were flipping quantum coins, the fair coin toss, or the operation that the beam splitter was carrying out in the experiment, can be performed with an operator called the Hadamard operator. So we also call this the H gate. And we're going to see we're going to see a bit about this. Okay, so first of all, I want to go back to our initial description of coins using probabilistic states and vectors. So in our classical case, we spoke of, let's say we had a coin facing head, and we did something like this, where we said this represents the vector 1, 0, where 1 here is the probability that our coin is facing head, and 0 here is the probability that it's facing tail. So from this, we just surmise that our coin is facing head. And we also had, we also had the case where we had a 1 here. A 1, and for that, we had a difference vector. So 0 here is probability that is facing head, and 1 here is probability that is facing tail. So because I have a 1 here, we can just say that our coin is facing tail. Okay, so now for our classical coins, sorry, for our quantum coins, we also have a representation here for head, and it's the 0 state. So the symbols you see here, when you see this, it's called the Ket notation. So when you see something like this, it just means that we're representing a quantum state as against a classical state. So initially, when we're representing our classical probabilistic states, we were using the symbols you see here. But now that we're discussing quantum states, we're going to use the Ket notation, which utilizes the symbols you see here. So we have the 0 states, and similarly, we also have the 1 state, which has the vector you see here. Okay, so just below, we're going to start exploring quantum circuits. So let me go back, and let me start off with the notebook you see here. Or first of all, let's even come here. So in case you haven't installed Qiskit, there is a notebook here for that. So you can run the cell you see here to check if your system has Qiskit, and you can run the next cell to actually install it. So once you're done installing Qiskit, then you can head over here to running your first quantum programs. So here, we're going to explore how to design a quantum circuit. So the first thing you notice here, I even used the term like not too long ago. I said Qiskit, and Qiskit is a library provided by IBM for designing and running quantum circuits. So from our Qiskit library, we can import a quantum register, and a quantum register is just our quantum memory, or the memory where we store quantum states or qubits. Okay, I haven't used the term qubits yet. Okay, so where we store quantum states. And we also have a classical register here where we store bits. So, okay, so similar to how with a classical register, we store the value, we store bits. Or similar to how in a classical register, similar to how in the memory of a classical computer, we utilize bits. In in the memory of a quantum computer, we utilize something called qubits. So a single qubit is the smallest unit of information in a quantum computer. And we have a circuit here. So in our quantum circuits, this is where we're going to introduce quantum operators to change the values we have in our qubits. Okay, so we've already said our quantum register here is our quantum memory, and we're requesting for a single qubit. And for our classical register here, we're requesting for a single bit. And we're going to introduce these to our quantum circuit. Okay, so I'm seeing a question. Where are those files?
We will send
Okay,
them.
okay, thank you. So we can introduce these to our quantum circuits. So now in our quantum circuits, we can now apply operators to change the values in our, or to change the values in our qubits. So here we have a single qubit, and because of that, so let me scroll up first. So we said our quantum memory or our quantum register here is represented by Q. So we have our quantum memory or quantum register, and it has several slots. So I'm just going to use 4 slots here. So the first location here is location 0, then location 1, then location 2, location 3, and we can go on and on and on. So I'm writing ... meaning we can keep going. So for the first location here, which is location 0, that's what we're trying to make use of. And actually, this is all we requested for. We requested for a single storage slot or a single qubit. So this is location 0. That's why we have Q and 0 here. So at this location, we want to apply an Qiskit. So the thing is that when we requested for the qubits or quantum, when we requested for the qubits, you see here, the initial value that we're going to have here is going to be the 0 state. So the initial value in our qubits is going to be the 0 state. And now want to apply an Qiskit. So an Qiskit is the same as the NOT operator. So we've already seen the NOT operator, and an Qiskit is the same as the NOT operator. So if we are to apply the NOT operator to the state you see here, which is the 0 state, we're going to get the 1 state. So if we are to apply the NOT operator to the 0 state, we're going to get the 1 state. So we can actually test this out. So we have measure here. We utilize measure to actually read the values we've stored in our qubits. So if we are to run this, so let me run this. Okay, so first off, we're even going to draw the circuits. So as you can see, it's the Qiskit that we're applying, and we have M for measurements, which is what we use to read out our values. And you can even use matplotlib to get a better looking diagram. Okay, so we've defined our circuits, and this is where we're going to actually execute it. Okay, so we're going to request for a backend So you can think of the backend here as the computer that we plan on running our circuit. And in this case, I want to utilize the QASM simulator. So the QASM simulator is, with the QASM simulator, I want to run my quantum circuit, but I want to run it on my PC, so which is a classical device. So that's why we have a simulator here, meaning it's a classical device, but it's simulating like the operations of a quantum device. So I'm simulating my quantum circuits on a classical device with the QASM simulator. And here we're setting shots. So short here is the number of times we want to execute our circuit. So in the case of tossing a coin, for example, this would mean we want to toss our coin 8,024 times. So this is how many times we're going to repeat our circuit. And then we can read out the results. So here we get 1. So we get 1 every single time. And that's because we started off with 0 and we applied an X, then we got 1. And then we measured here to check the results. So we repeated this 8,024 times. So obviously every single time we're going to get 1. So here we even have larger circuits. So we're requesting for 4 qubits here and 4 bits. And then we can introduce them to our circuits and apply operators. So we're applying the Qiskit or the NOT operator. And we can even draw out our circuit. So we applied the Qiskit a couple of times, as you can see here. And if we are to check the results, so in this case, we repeated it just 100 times. And every single time, we got 110. Every single time, we got 110. And, okay. So let me run this. Okay, it's actually correct. Oh. Okay, so as I said just now, every single time we got 110. And if you look at the circuit here, we started off with 0. Then we applied an Qiskit, then we got 1. Then here, we started off with 0, applied X, we got 1. Applied X again, we got 0. Then applied X again, then finally we got 1. So here, 0, 1, 0, 1, 0. Then here, 0, 1, 0. So finally at the end, we have 1, 1, 0, 0. And that's what we got, 1, 1, 0, 0. So if you're not getting results like you see here, that's because, okay, if your circuit doesn't look how mine does here, that's because I'm setting reverse bits here to true. So if you don't do that, it's going to look it's going to be organized in the version you see here, where we have 1, 1, 0, 0 instead. So you have to read it from the bottom to the top in that case, if you don't set reverse bits to true. Okay. So I'm just going to go back to the Hadamard operator that we were just looking at. Okay. So here, we now have a circuit. We have a circuit with a single qubit, a single bit, and we want to apply an operator. But in this case, we want to apply the Hadamard operator or the H gate instead of the X gate. And that's the circuit you see here. So we have the H gate instead. So we said the H gate is the H gate does something similar to what the beam splitter does. So we can think of the H gate as tossing a fair coin. And if we are to do that, so here we set short to 10,000. And when we checked our results, we ended up with 0 or head 5,064 times, and we ended up with tail or 1 with 4936. So as you can see, it's quite close to 50% for each side. So this is from a single toss. And if we are to even try out the third experiment where we performed 2 tosses, so here, as you can see, we've made use of a H gate for the first toss and another H gate here for the second toss. So we have 2 coin tosses, and if we check our results, every single time it lands, it's going to land on head. So with the experiment here, it's consistent with the diagrams we drew. So if anything is not clear, feel free to ask questions, preferably on Discord. But you can also put up your hand here and ask your question. Okay, so let's move on to 1 qubit. So when we're running the circuits, we already spoke about what a single qubit is. And we said, similar to how we utilize bits in a classical computer, we also have qubits in a quantum computer. So in a single qubit, we can store the 0 state, for example. So in a single qubit, we can store the 0 state or even the 1 state. Similar to how in a classical computer, we can store the value of 0 or 1. Okay, then so here we have the NOT operator. And in the first experiment we carried out, we saw how the NOT operator just flips 0 to 1. So the NOT operator can be represented with the matrix you see here. And if we are to perform some matrix vector multiplication, so we have the matrix for the NOT operator here, and then we have the 0 state. So if we are to perform some matrix vector multiplication here, the vector we end up with is the vector for the 1 state. And we also like tried out the reverse, where we have the 1 state and we perform the matrix vector multiplication and we end up with the 0 state. Okay, so we just looked at the matrix form of the NOT operator. And now let's look at the matrix form of the Hadamard operator. So for the NOT operator, this is like consistent with what we had in the classical this is consistent with our classical version of the NOT operator. So when we're looking at probabilistic states and probabilistic operators, for the NOT operator here, this is exactly what we would have used. This is exactly what we would have used to perform this. Okay, so to execute the NOT operator, this is the exact same matrix we would have used in our classical experiments. But for the Hadamard operator, it's not consistent with what we had with the fair coin flipping operator. So when we're looking at the fair coin flipping operator, this was what we had as its matrix. So this is what we had as the matrix for the fair coin flipping operator. So if we are to multiply what you see here with the probabilistic state for head, for example. So if we are to perform some matrix vector multiplication here, we're going to get 1 over 2, 1 over 2. So this is what we got. And this is the probability that lands on head, and this probability lands on tail. So this is what we described when we were looking at our probabilistic operators and probabilistic states for a fair coin toss. But if you look here, we have something different. So here, instead of 1 over 2, we have 1 over root 2. So we have different values here. And we even have a negative entry here, which is dissimilar from what we saw for our probabilistic operators. So for our probabilistic operators, we said we shouldn't have negative entries. And we even said the columns should sum up to 1. But we have something different here. Okay, so here we're applying the Hadamard operator to the 0 state. And when we do that, this is what we get. So here we have a quantum state, and it looks different from our probabilistic states because the entries here, they don't sum up to 1, as you can see. The entries here, they don't sum up to 1. So we can't say each entry is the probability of some outcome. We can't say that. We can't say each entry here is the probability of some outcome. We can't say that. But even though these are the entries we have, from experiments, the probability that it still lands on head is still 50%, and probability that it lands on tail is also 50%. So although these values are in probability values from experiments, we still have results that are similar to what we have in a classical experiment. So these values, although we can't directly call them probability values, we can utilize them to get the actual probabilities for certain outcomes. So for the 1 over 2 you see here, even though it's not directly a probability value, if we are to square the value you see here, we're actually going to get 1/2, which is the actual probability. So the entries of the vector you see here, so this is our quantum state. So for these entries, to get the actual probabilities for certain outcomes, in this case, the first entry here, we're supposed to use it to get the probability that our coin will land on head. So if we are to square it, we're going to get 1/2, which is the probability that our coin lands on head. And similarly for the lower entry, when we square it, we get the probability that it lands on tail. So if we are to even multiply the Hadamard operator with the one state, this is what we get. So the entry share, they aren't the actual probability values because they won't sum up to 1. But to get the actual probabilities, we need to square these values. So if we are to square this, we'll get 1/2, which is the probability that lands on head. And also for the lower entry, if we are to square minus 1/2, if we are to square this value, then we get the actual probability that it will land on tail. So when we apply the Hadamard operator to the 0 state, the quantum state you see here is what we refer to as the plus state. And the quantum state you see here is what we refer to as the minus state. Okay, so I think I have a question. So we have a quantum state in a single qubit. And we have a quantum state in a single qubit. And if we were to utilize the same coin analogy here, what's the probability that our coin will land on head in the quantum state you see here? So what's the probability that our coin will land on head from the quantum state you see here? So you can type in the chat. So we have a quantum state here. Okay, so 9/25, 9/25. Okay, thanks. So as we said, the entries you see here, they are the amplitude values, and even if you sum these, as you can see, it won't sum up to 1. So to get the actual probabilities, we need to square the entries. We need to square the entries. So for this, if we are to square the value you see here, we're going to get 9/25, which is the actual probability value. And here, if we are to square this, we're going to get 16/25. So this is the probability that our coin lands on head, and this probability that our coin lands on tail. And if we are to sum it, we end up with 1. So for our quantum states, we can have negative entries, and they don't sum up to 1. It's only when we square the entries and sum them up that we get 1. Okay, so let's move on to the next notebook. Okay. Okay, so I have a question. So the state you see here is this state a valid quantum state? Is this a valid quantum state? So the state you see here is this a valid quantum state? Okay, because when we were looking at probabilistic states, we said the entries should sum up to 1. So for us to have a valid probabilistic state, the entries should sum up to 1. And they should also have non-negative entries. But for what we have here, is this a valid quantum state? Okay, so I think everyone agrees that it's not a valid quantum state. And actually, the answer to my question is even written here, even underlined. So, so this is not a valid quantum state. And yes, if we are to square these values and sum them up, we're going to get we're going to get 2. So it's not a valid quantum state. Okay, so yeah, let's try one of these. So for this one, what's can be the value of B to make this a valid quantum state? I guess for the people that actually have Jupyter Notebook set up and are going through the content, they can just click for the solution. But what value of B what's the value of B that will make this a valid quantum state? Okay, so most people are going with 6. Okay, so let's see. Let me test this out. 6/5. Okay. So let's test this out. If we are to square this, we get 1/2. If we are to square this, we get 1/3. So if we are to sum these, we get 5/6, if I'm not mistaken. Five over 6. And then if we take, or let me put it in this form. Then if we take these, I think it might look something like this. So let me check. I'm entirely not sure. I hope my math skills don't fail me now. Okay, so let's see. I think I just might be doing something wrong, but okay, so I think I should run this. Oh, I was terribly wrong. So where did I go wrong here? Square this. Okay, I didn't square this. But if I was to square this, or I missed something here. So we're printing out. Oh, okay, okay. Hmm. So let me see. If I'm to divide 5 by 6, okay, so this is definitely 5 divided by 6. And this is what we have left. Okay, 1 over 6. Okay, I didn't subtract properly. Yeah, I definitely didn't subtract properly. Whatever I was doing there. Oh, yes. I added, but I didn't subtract. True. Okay, okay. Yes, yes, yes. Okay, that makes sense now. So yes, this is definitely 6. This is definitely 6. Okay. So moving on. So for our quantum operators, because we've already like defined the property where we said if, okay. Okay, so although I'm still going to like redefine this rule a bit when we get to the next notebook. But for now, we have the rule whereby if we are to square these entries and sum them up, we said they should sum up to 1. So for all our quantum operators, they should be length preserving. They should, all our quantum operators should be such that if I was to apply our quantum operator, let's say the Hadamard operator, to some quantum state, the results I get, it should still be a valid quantum operator. So the length of the vector you see here should still be 1. So c square plus d square should be equal to 1. Okay, yes. C square plus d square should be equal to 1. So our quantum operator should still obey this rule. Our quantum operator should be length preserving, such that if we apply it to any quantum state, the results we get should still obey that rule. Okay, so let's move on to the next notebook. So let's move on to visualizing a valid quantum state. So thus far, we've looked at the 0 state and we've looked at the 1 state. But we can also have the minus 0 state, whereby 1 has a negative sign in the vector here, and also for the -1 state, the 1 here also has a negative sign. Okay. So now we want to visualize the quantum states in a single qubit. Is that the best way to phrase it? Yeah, once you visualize a single qubit, or once you visualize the states we can store in a single qubit. So the rule that we defined earlier was this. We said a squared plus b squared is equal to 1. Okay, so let me just point out here that the entries in the quantum states that we're going to be looking at, they are strictly going to be real numbers. So these entries are only going to be real. That's why defining the rule in this form. We can also have complex entries, and if that's the case, we're going to be talking of the magnitude squared. But since we're only looking at real entries for A and B, I'll just do away with this. So for real values of A and B, we can actually use a unit circle to visualize the states in a single qubit. And we're going to see how. So we've already said that this is a unit circle. So the radius of our circuit here, of our circle here is 1. So because it's a unit circle, we know that the radius here is 1. So from this, we're going to create a right angle triangle. And for our triangle here, we have one of the sides as A and the other side as B. Okay, and from Pythagoras theorem, we know that the adjacent side squared plus, okay, I don't really say that out, but we have the adjacent side squared plus the opposite side squared should be equal to the hypotenuse squared. But obviously, 1 square is 1. Okay, so for an angle theta here, we can say cos, cos theta is equal to the adjacent side over the hypotenuse. But dividing by 1, we're still going to get exactly the same thing. So I'll just leave this as A. And for sine theta, we have the opposite side divided by the hypotenuse, in this case, which is 1. So anything divided by 1 is exactly the same thing. So we have B here. And we can even write cos squared theta plus sine squared theta is equal to 1, which is a famous trig identity. So this is correct. So for our vector here, I can just replace A with cos theta. And B here with sine theta. Okay, so you can think of this as a general form for our quantum state. You can think of it as a general form for the quantum states we can have in a single qubit. And we're sticking to just real values here. So for cos theta, we just need to divide, okay, so for the entries you see here, we just need to define an angle, and then we get our vector. So what that means is that we have a circle here, and just by specifying the value of theta here, we can touch any point on our circle. So if I was to draw these points, we have a new value of theta, a larger value of theta. And if I was to increase theta again, I can even end up here. And we have a new vector, which is also going to be a valid quantum state. So just by changing our values of theta here, we can end up at any point on the circle you see here, and it's still going to be a valid quantum state because this rule is still going to be true. Okay, so if we are to scroll down, okay, so we even have a circle here with all these dots. So any point you can pick out here, any color you can pick out here is going to be a valid quantum state because it's a point on our circle. So all these vectors you see here, yeah, really colorful. They are all valid quantum states because they are all, these are all vectors of unit length. So to actually define a couple of vectors we've already seen on the unit circle, as we've described it here. For the zero state, this is where it's located. And because for the vector you see here, it has the values cos. So theta here is 0. This is our starting point. So cos theta here is 0. Theta here is 0. So we'll have to calculate cos 0 and then sine 0 also. And this is going to give us 1, and this will give us 0. So for the vector you see here, we know this to be the 0 state. And this is the location for the 0 state, as you can see. Then for the location you see here, so our value of theta here is going to be pi over 2. So we're going to calculate cos pi over 2 or cos 90. So here sine pi over 2 or sine 90. If we are to calculate these values, so what we get from this is going to be 0, and what we get from this is going to be 1. And this is the 1 state as we know it. Okay, so we can actually try this for a couple of angles. And so as you can see, at this location, we get -0. So by attaching a negative sign to the 0 state, we have a vector pointing in the opposite direction. And also attaching a negative sign to the 1 state, we also have a vector pointing in the opposite direction. Okay, so another state that we've seen is the plus state. So we've seen the plus states, and we said this is what we get when we apply the Hadamard operator to the 0 state. So if we are to apply the Hadamard operator to the 0 state, we're going to get the plus state. So for the plus state, it has an angle or theta here in the plus state. Theta is equal to pi over 4. Theta is equal to pi over 4. So we have cos pi over 4 cos pi over 4 is 1 over root 2. And sine pi over 4 is 1 over root 2. So the vector you see here is actually what we defined the plus state to be. And we can actually try this out for the minus state also. So for the minus state, we have an angle of minus pi over 4, and here also minus pi over 4. So if I was to calculate this, we're still going to get 1 over root 2 here and minus 1 over root 2 here. And what we have here is the minus state. Okay. Okay, so a question for the chat. At this location, we have the minus state. So a question for you guys. At this location, we have the minus state. So what's theta at the minus state? What's the value of theta at this location? So this is something you can just type in the chat. What's theta at the location of the minus state? Also for the minus plus state, we have the vector pointing in this direction. So what's theta at this location also? Okay, so I'm seeing 135 degrees or 3 pi over 4 for minus. And I'm seeing 225 and 5 pi over 4. Okay, I'm seeing minus 3 pi over 4. Okay. Okay, so we already know that this is pi over 2. And then we have pi over 4 here. So if we are to sum these, we're going to get 3 pi over 4. Okay, so this is correct. So this is also the same as 125 degrees. And for the location here, so we have pi, and then we have pi over 4. So we have pi plus pi over 4. So this will give us 5 pi over 4. So this is correct. So thank you. This is correct. And it's also the same as 2 to 5 degrees. Okay. So thus far, we've been talking of quantum systems. We even saw classical computers yesterday, or we spoke briefly about classical computers yesterday. So at this point, you might even want to ask if we already have classical computers and they work with memory, and we apply operators to change the values we stored in our memory, and we read out results. And similarly, in a quantum computer, we have memory, we apply operators to change the values we stored in memory, and we read out the results. Why do we even need quantum computers? Like, what makes them beneficial? So here, there are 3 resources that we can utilize in a quantum computer that are not available in a classical computer. And with these resources, we're going to try and get some advantage over classical computers. So, okay, well. So I'm going to start off with superposition. So let me try and explain superposition. So that's even the next notebook that we're going to take a look at here. So this notebook is on superposition and measurement. So let's look at superposition. Let's look at superposition. So the classical computers, how we utilize classical computers is by storing bits. So our bits can take on the values of 0 or 1, and then we apply operators to change these values, as we already know. So our classical computers don't even utilize probabilistic states or probabilistic operators. We just have zeros and ones and deterministic operators to change these values. Even when we have functions that seem random, under the hood, everything is still kind of deterministic. So for our quantum computer, we've already said that if I was to apply an operator like the Hadamard operator, for example, so we said the Hadamard operator is something like a fair coin toss. So if I was to do that, there's going to be some probability that my coin can land on head and some probability that my coin can land on tail. So while my coin is still spinning in the air, it's in a state of superposition such that there is some probability it could land on head and some probability it could land on tail. So the vector you see here, I'm going to like write it in linear form. So I have A here with I have A, that's my amplitude for the 0 state. And I have B, which is my amplitude for the 1 state. So what I have here is a superposition such that there is some probability that if I was to read out my results, it can be 0, and there's some probability that it can be 1 if I was to read out my results. So at this point, okay, so at this point, there are actually 2 ways that it's clear to us that superposition provides us with some. Superposition is a powerful quantum resource that is advantageous as against like working with a classical bit. So with a classical bit, we said in a classical bit, we can have the value of 0 or 1. So in a classical bit, we're limited to just 2 values or 2 possible values. Those are 0 and 1. But because of superposition okay, so like let me. So the vector is here, and the vector is here should be a valid quantum state. So as long as it's a valid quantum state, it's something we can store in a single qubit. So as against the case for a classical bit, where we're limited to just 2 possible values, in a qubit, we can have the 0 state, we can have the 1 state, and we can have any other state as long as this rule is as long as we follow the rule whereby a squared plus b squared is equal to 1. So as long as this rule is obeyed, this is a possible value that we can store in a single qubit. So ideally, the different possible values we can even store in a single qubit, it's infinite. So in a classical bit, there are just 2 possible values. But in a qubit, ideally, we can store an infinite different possible number of values. Okay, so because of A and B here, the space for the different possible values the space for the different possible values we can store in a single qubit is practically infinite. Sorry, is theoretically infinite. And the next thing is like, because we have the plus sign here, what we're trying to say is that if we were to perform some computation, it's kind of like we're supplying both values at the same time, because we're saying, okay, there is some probability that is the 0 state and there's some probability that is the 1 state. So we're kind of supplying both the 0 states and the 1 state at the same time for some computation. So let me try and explain what I'm trying to like describe here now. So let's say I had a couple of constraints. Let's have a couple of constraints that I want to use to find some number. And for my constraints, let's say I want the number I'm looking for should be less than 16. It should be an even number. So it should be less than 16. It should be even. No, sorry, it should be odd. Let's say less than 16. It's odd. It should be divisible by 3. So it should be divisible. I'm not even sure I can spell divisible. It should be divisible by 3. And maybe greater than 12. So I've placed a couple of constraints for a number I'm interested in. Okay. So, okay, first of all, because I've said, okay, I've placed a couple of constraints for a number I might be interested in. So one possible approach I could take for this is that, let's say I had a classical computer that can like utilize just a single process. So I might have to get like, let's say 15 separate computers now to check. Okay, or no, sorry. Okay, so let's have like a single computer now that is running a single process. If I was interested in finding a number that meets all these constraints, it will start checking. Is the number 0, for example? No. Is it 1? No. Is it 2? No. 3? So it's going to be counting sequentially up until it gets to a number that meets these constraints. That's one possible approach. I have a single computer running a single process, and and the computer is going to be checking sequentially for numbers that meet these constraints. But I might also have the case whereby I have maybe 20 of these computers. So instead of having one computer having to check all these numbers sequentially, I can just tell the first computer, okay. Yeah, let me just, so I'm just going to write like a couple of squares. So each square here represents a computer. This is not, I'm not like talking of storage now with the squares. Each square here represents like a computer. So I have like 20 of these, and I can tell, okay, so the first computer here can check if 0 meets these constraints. The second can check if 1 meets these constraints. The third can check if 2, 3, up until the 20th computer can check if like 19, for example, meets these constraints. So this is parallel computing. And so to do that, I needed let's say 20 computers, or maybe I didn't even, okay, let's say I had 16 computers, and I can check up until 15. So they can all do this in parallel. They are all assigned some number, and they can check to see which one meets the constraints. So the final computer here, so 15 meets all these constraints, and this computer will be like, okay, yes, 15 is the correct answer, and to provide it to me. So here we performed parallel computing. We didn't have to like check the numbers sequentially. Each computer here was able to check was able to check a single number, and the one that had the correct answer will like, I don't know, call out to me and be like, yes, I've gotten the right number that meets these constraints. Okay. But for our classical computer, for our quantum computer, we have just a single quantum computer. And what we're going to do, so we have a single quantum computer, and what we're going to do is that we're going to create a superposition. So we're going to create a superposition, and okay, so for this superposition, utilizing utilizing 4 qubits. I'm utilizing 4 qubits for this superposition. I hope I calculated this right. Not sure. But so what we're going to do is that for our 4 qubits, when we create an equal, or when we create a superposition for our 4 qubits, so here, as you can see, I have 0, I have 1, and all the numbers in between up until 15. I have all of these in superposition. So my vector will actually be a 16, or my vector will actually have 16 entries in it, and that will provide a superposition, as you can see here, for all these states. That's from 0 up until 15. So instead of having to pass all these numbers individually, I can just pass the state you see here as a single entry into my quantum computer. So this is not parallel computing, but I'm not sequentially providing the different inputs to my computer. Like, there's some probability that it's 0, some probability that it's 1, some probability that it's 2, 3, 4, up until 15. And what we have here is a single entry that I'm going to pass to a single quantum computer, and it's going to check, and I can set up some algorithm here such that it checks all these numbers for the one that meets the constraints you see here. So I'm not like sequentially passing the numbers one after the other. I'm just going to create a superposition of all these numbers and pass them at once, and it will check them for the number that successfully like meets the constraints that I'm interested in. And in that case, that would be 111 here. So when I'm able to find this number, the next thing that I would want to do is to like perform, or the next thing I'm going to utilize is the quantum resource or quantum effect of interference, whereby I want to cancel out all these other entries, and 111 is the only thing that is going to remain. So we're actually going to look at interference now. I just want to point out that it's through interference that we're going to like cancel out all the other entries in our superposition, and only 111 will remain. And at the end, when we read our results, we'll see that 111 is the right number that meets these constraints. Okay, so let me check the chat if there are any questions or something of the sort. Okay, so I think okay, yes, so I think
Thank you,
all the
Kenneth.
questions, yes, I think all the questions were answered in the chat, so thank you.
Thank you. So we're done for today for the notebooks.
The only thing I have to just point out, or no, I'm going to round up in, let's say, 5-minute stops. I'll be done.
Okay.
So let me just like quickly go over this and I'll be done. Okay, so for the third experiment we saw earlier, whereby we utilized 2 Hadamard gates, and every single time we measured, we always got 0. We were actually utilizing superposition and interference. So we're going to see how this works. So we start off with the 0 state, as you can see here, and then we apply the Hadamard operator, and this is what we get. So we now have a state in superposition, which is the plus state, as you can see here. We have our state in superposition. And then the next thing that we're going to do is that we're going to apply the second Hadamard operator. So when we do this, so okay, so we have the plus state here. We have the plus state here, and we're going to apply the Hadamard operator to the plus state. So this is a linear system. So we're just going to apply h to 0 here and h to 1 here, as you can see here. So applying h to the 0 state, this is what we get. And applying h to the 1 state, this is what we get. We'll also multiply with these values. So if you look, we have the 0 state here with only positive coefficients, while the 1 state here has a positive and a negative coefficient. So for the 0 state, these values will like reinforce themselves, or they will interfere constructively. Whereas the 1 state here, these will cancel themselves, or they will interfere destructively. And that's how we end up having just 0 at the end. So this is like interference in action. For what we're interested in, the 0, for example, in this case, it's supposed to interfere constructively, whereas 1, which is what we might not be interested in, it's supposed to interfere destructively and cancel out, and we only end up with 0 at the end. So the only other thing here is on measurements. And so measurements is how we actually like retrieve results from our quantum computer. Because for our quantum states, we can't directly read or retrieve the values as they are stored in our quantum states. So in the case of like a spinning coin, we can't look at a spinning coin and tell if it's like a fair coin or if it's a biased coin, and if it's biased by like how much. So to actually retrieve values from our spinning coin, for example, we need the coin to land and see if to land on head or tail. And we can repeat this a couple of times. So when it lands on head or tail a couple of times, we get some distribution. So we calculate the number of head we get and the number of tails we get, number of heads we get and number of tails we get. And from that, we can try and reconstruct our quantum states. So measurement is just like letting our coin land and reading out and checking the value. So that's why in our circuits we were using qubits and bits. So we had a quantum register and a classical register. So when we perform measurements, we're just transferring information from our qubit to our classical bits, and we'll now retrieve the results from our classical bits. And as you can see, we were getting some distribution for, okay, so here we had a certain number of zeros and a certain number of ones. And from this, we'll now try and reconstruct the quantum states that was there before we measured. So measurements, you can also call this like the collapse of the wave function or collapsing the superposition. So when we measure and our quantum state ends up in either the 0 state or the 1 state, it stays there until we apply some other operator. Okay, so I guess that's pretty much everything that I wanted to cover.
Thank you, Kenneth.
Yeah, thank you. Thank you, Yanis.
So let me stop the recording here for the lecture. Or
Okay,
do
sorry,
you
please.
want to continue with the panel? Do you
Okay,
want
yes,
to
we
take
can
a
continue the
break,
panel.
like some minutes break, and then we go on with your panel? What do you think, Bruna?
I believe if it is okay for the panelists, for me is okay as well. So if you can just send a reaction or something.
Maybe we should add the panelists to the panel
Oh,
here. I don't know.
everyone's here already.
Okay. Sorry, I
So
didn't.
I don't know. I
Okay,
think we can give a break. Just let me know. I guess we can give a 5-minute break then,
yeah.
since
Let's,
everybody's here.
so I don't stop the record. You will have the panel recorded also.
So for me, it's fine.
Okay.
Also, once again, if someone else don't want to be recorded, let us know.
Okay. See
Perhaps
you.
if it is possible, I to split the recording in 2 parts, because I
Yes,
think the part that
Okay.
will be.
Then I
Sorry?
will stop this recording here.
All right, then it's okay, because the